Okay, so this was number 2 from last night's homework. So if you plug in the 0, you end up with 0 over 0. I'm not going to show all the work that makes that true, but it is true. So we decided yesterday that the right way to go about some of these was doing a U substitution, where U is equal to the thing inside the cube root, or the whole cube root. So even though this one has a squared on it, we're just still going to make the U value the cube root of x plus 27. And then that would tell us that x is equal to U cubed minus 27 if you cube both sides and then subtract the 27. Okay. And it also tells us that when x is approaching 0, U is approaching the cube root of 0 plus 27, or 3. And so this gets rewritten as the limit as U approaches 3 of 2 times x squared. And this is the part that I believe every single person that asked me about this question had screwed this exact same thing up. So most people that, well, like I said, everybody that asked me about this just wrote U cubed minus 27 there, and they forgot that x is supposed to be squared. So don't forget to square that if there's a squared up there. And then this became U and then squared minus 6U plus 9. So everybody good with that?
Yeah.
Okay. And then the U cubed minus 27 is a difference of cubes. I would go through when I show all my work on the actual answer key, you'll see that I plugged in 3 here and got 0 over 0 again. So I'm just going to make a note that 0 over 0. And so then we factor our difference of cubes. So we get the 2 out in front still, and then it's U minus 3, which is going to be squared because it's squared on the U cubed minus 27, and U squared plus 3U plus 9, which is also going to be squared. And then down in the denominator, that factors to U minus 3 squared. The U minus 3 squareds will cancel, and we got the limit is U approaches 3 of 2 times U squared plus 3U plus 9 squared, or 2 times 3 squared plus 3 times 3 plus 9, all of that squared, which, let's see, that's 9 plus 9 plus 9, that's 27. 27 squared ought to be 829, I believe. I mean 729, that's how you multiply. And then if you multiply that by 2, you end up with 1458. Good or no?
Good.
Okay. Cool. All right. Number 5 was also a question here. So we got the limit is n approaches 2 over 1 over n squared plus 1 minus 1/5 all over n minus 2. So if you plug in 2 to that, that becomes a fifth minus a fifth over 2 minus 2. So 0 over 0. And so what we did the other day was we found a common denominator. So the common denominator of the numerator will be n squared plus 1 times 5. So we're going to rewrite this as the limit as n approaches 2 of 5 over 5 times n squared plus 1 minus the quantity n squared plus 1 over 5 times n squared plus 1 in the numerator. So I multiplied the first part by 5 over 5 and the second part by n squared plus 1 over n squared plus 1. And then dividing that by n minus 2 over 1, which means we're going to take the reciprocal and multiply. So everybody good so far with that?
Yep.
Okay. The 5 minus the n squared plus 1, you got to distribute that minus sign to both of those. So 5 minus n squared minus 1 over, and then we got a 5 times an n squared plus 1. And then we're multiplying by 1 over n minus 2, so that's going to put an n minus 2 down there also. And once again, if we plug in the n approaching 2, this is going to become 0 over 0. What does 5 minus n squared minus 1 become? That ought to just become 4 minus n squared. which ought to become 2 minus n, 2 plus n. And we would note that the 2 minus n and the n minus 2 are almost the same thing. All we have to do to get those to cancel out, and that's what we want to cancel because that's what's causing the problem with the 2, is to factor a negative out of that numerator. So we're going to say this is equal to the limit as n approaches to the opposite of, and we factor out the negative from the 2 minus n to give us n minus 2. And then we got 2 plus n, and we got 5, and we got n squared plus 1, and we got n minus 2. Cancel those out. And if we plug in 2, we got negative 4 over, what does that become? 2 squared is 4 plus 1 is 5 times 5 is 25. Any questions or issues with that one?
No.
No, everybody good there? All right. And then I think the last one somebody was asking about was number 10. Number 10 was another one of those fun substitution ones, right? The limit as x approaches 5 of the cube root of x plus 3 squared minus 2 cube roots of x plus 3 over the cube root of x plus 3 squared minus 6 cube roots of x plus 3 plus 8. So I'm not going to go through the whole process of showing that it's 0 over 0, but it is 0 over 0. And then we'll do the substitution where u is equal to the cube root of x plus 3, and x is equal to u cubed minus 3. Everybody good with that? As x approaches 5, u approaches 2, because 5 plus 3 is 8, and the cube root of 8 is 2. Good or no? So far?
Good.
Okay. So we end up with the limit as u approaches 2 of u squared minus 2u. I guess we didn't need what the x was now that I look at this here again. U squared minus 2u over u squared minus 6u plus 8, which is still, I'm guessing, 0 over 0. Yeah, 4 minus 12 plus 8. Yep. Should still be 0 over 0. So now we just factor. And the u minus 2's will cancel. And plug in your 2.
Mr. Bachelor,
What's that?
do we have to show that it's still indeterminate at that second step?
No, it's not a huge deal if you don't do that. I don't really care. I mean, there's nothing wrong with factoring it and canceling stuff out, even if it's not. So,
Okay, cool.
all right, so we got 2 over negative 2 there, which ends up being negative 1. Any problems with that? Any questions with that? All right. Let's then get into some new stuff for today. Today is going to be, we redo that last problem from the other day, so we're going to do it in a different way. Practice some stuff similar to that, and then we're going to move into a bunch of rules for limits that we need to know. So this is the same problem we had on Tuesday, right?
Yes.
Okay. So On Tuesday, we just drew the graph of this and did it graphically. But today we're actually going to go through and do this algebraically. So we're looking for the limit as x approaches 0 from the left of f of x, right, with our little negative sign. This is the one-sided limit of absolute value of x over x. So if x is approaching 0 from the left-hand side, what does that tell you specifically about all of the x values?
They're negative.
They're always negative, right? X is always less than 0, no matter what. Every x value is less than 0. So we need to think a little bit about the definition of absolute value. Are we all familiar with the algebraic definition of absolute value? Which is not make it positive. That's not the algebraic definition of absolute value. We're familiar with the absolute value definition or no? No? Yeah, maybe. Sounds like no, since no one's responding.
Not completely.
Not completely. Okay, let's get a new page here. There's two ways to sort of define absolute value. One is geometrically, right, which is like on a number line. Right. Geometrically on a number line, what's the definition of absolute value?
Distance from 0.
Right, it's just the distance from 0. Absolute value is the distance from 0 that our point is. So like if here's 7, the absolute value of 7 is 7 because 7 is 7 units from 0, right? Here's negative 10. Well, the absolute value of negative 10 is 10 because the distance from 0 is 10. Easy enough?
Yeah.
Okay.
Yeah.
Now, that's geometrically. Algebraically, and that's probably what you like originally learned a long time ago when like you did absolute value in first grade or something. Algebraically, you should have learned, which nobody probably ever taught you, that the absolute value of x is equal to x. And when is that true? If x is greater than or equal to 0. Would you agree with that?
Yes.
If I take the absolute value of 0, I'm 0 units from 0, and the absolute value of it is just itself. If I take the absolute value of 7, well, that's just 7. It's just the number that I was taking the absolute value of. But what is the absolute value of x if x is less than 0?
Negative x.
Right, it's the opposite of x, right? The absolute value of negative 10 is the opposite of negative 10, it's 10, right? Because x is less than 0. We have to take the opposite of it to find that distance from 0. So this algebraic definition of absolute value is actually really important in solving some of these calculus problems. So here we're talking about x values that are less than 0. So this is asking us what's the limit as x approaches 0 from the left of the absolute value of x over x. Well, when x is less than 0, what does the absolute value of x actually represent?
Negative x.
It's negative x, exactly. So negative x over, well, x is just x, right? And this obviously is indeterminate, 0 over 0, right? So what do? We cancel the x's. This becomes the limit as x approaches, sorry, I should still have that from the left there. The x approaches 0 from the left of negative 1, which is just what do you think the limit as x approaches 0 from the left of negative 1 is? Here's negative 1. So I approach 0 from the left-hand side.
Negative 1.
Yep, it's just negative 1. And a little bit later on today, we're going to talk about finding the limit of a constant, which is actually much easier than all the other limits we've done. The limit of a constant is always just the constant, right? Because a constant is just a horizontal line. The y value doesn't change, so the limit at any x value is just that value, that y value. Everybody good with that? And that's the same answer we got yesterday, right? By looking at it graphically?
Yes.
Cool. All right. Well, now, if we're looking at the limit as x approaches 0 from the right of f of x, that tells you that all of the x values are positive. So the limit as x approaches 0 from the right of absolute value of x over x ought to be the limit as x approaches 0 from the right of, what happens to the absolute value? It just becomes
1.
x over x, and then those cancel. Yeah. And you get 1. And then therefore, the two-sided limit doesn't exist. Everybody good with that or no?
Yeah.
All right. So you should be able to solve these both algebraically and by looking at the graph. And either way is acceptable. Just know how to do both ways. So what if I was asking you to find the limit as x approaches 7 from the left of the absolute value of x minus 7 over x minus 7? First off, each one of these is indeterminate, right? From the left, from the right, and the two-sided limit, they're all indeterminate. Would you agree?
Yeah.
Yeah. So it means we got to do a little extra work. And if x is approaching 7 from the left, that's telling us that x is less than 7, which is telling us that x minus 7, the thing that's inside of our absolute value, is less than 0. So the thing that we are taking the absolute value of is a negative number, which means that the absolute value of it is the opposite of it. So this becomes the opposite of x minus 7 over x minus 7. Everybody good with that?
Yes.
Okay. This is the one page I said I added into today's notes, for those of you wondering where this page is. So now we just have the limit as x approaches 7 from the left of -1, which is -1. And what about this one? As x approaches 7 from the right, x is greater than 7, which tells us that x minus 7, the thing inside the absolute value, is positive. And so its absolute value is just itself. And clearly we can cancel those out to give us the limit as x approaches 7 from the right of 1, which is 1. And what does that tell you about the two-sided limit?
Does not exist.
It does not exist. All right. Everybody feel okay about that? This idea of this algebraic definition of absolute values it's important, especially in limits, because it pops up with limits like these, but it's also going to pop up with some other more irritating limits that we're going to deal with probably tomorrow, is my guess. So we got to make sure we understand that definition of absolute value. All good?
Yeah.
Let's look at a really fun and exciting piecewise defined function. So we've got f of x equals, and then all this other crap. 3 minus x if x is less than 1, 4 if x equals 1, and x squared plus 1 if x is greater than 1. And we want to find the limit as x approaches 1 from the left and from the right, and if it exists, the two-sided limit. Conceptually, everyone good with what we're doing?
Yes.
Okay. So we're going to do it algebraically first, then we're going to just graph this and just sort of see what it looks like also. So if we're looking for the limit as x approaches 1 from the left of f of x, that's telling us that x has to be less than 1, right? So as we approach 1 from the left-hand side, which piece of this function are we going to be using?
3 minus x.
3 minus. So this is the limit as x approaches 1 from the left of 3 minus x. And, well, what is that? It's just 3 minus 1, right?
Yeah.
What about as we approach 1 from the right? That's telling us that x is greater than 1, and therefore we need to use the piece where x is greater than 1. So this is the limit as x approaches 1 from the right of x squared plus 1, which is just
2.
1 squared plus 1. Or... Good?
Mm-hmm.
And what is
4.
got to be the left is 2 and the limit is 2. That means that the two-sided limit is 2. Remember we had that rule way back the other day. Okay. The limit as x approaches a of f of x is equal to L if and only if these two limits. So since the limit on the left was 2 and the limit on the right was 2, then two-sided limit is also 2.
Wait, what's the point of saying 4 for x equals to 1 then?
Well, let's take a look at the graph. So 3 minus x when x is less than 1. Well, 3 minus x. Pretend that linear line is actually linear. And then our function equals 4 at x equals 1. And then we have x squared plus 1, which well, would look like a parabola, right? It would go, kind of go up like this, right?
Yeah.
So that point at the point 1, 4 is the value of f of x at x equals 1. But it is not the limit. It's not what we approach as we approach the left. Right. Remember way back at the beginning, we did that. I think we were dealing with like x plus 2, and then we looked at a rational function that had a hole at 2, and then we put another point in also that didn't fill in the gap. It's all about what happens as we approach the point, not what happens at the point. We don't care that it's 4 there. It could be a million. You know, I could have said a million when x equals 1, and the limit would still be 2, because as we approach 1 from both the left and the right, we're getting very close to 2, and we can get as close to 2 as we want by picking x values very, very close to 1. Even though when we get to 1, the actual value is 4, that doesn't matter.
All right, wait. So if what if limit of x is less than 1 and then the limit of x greater than 1 is different, but then there's still a given point for x equals to 1? If that was the case, then would the limit be what the value of x equals 1?
No, it would not be. That limit would not exist. The
All right.
limit from the left, the limit from the right have to equal the same number for the otherwise it cannot.
All right.
All right, pretty good.
Yeah.
Okay, so like I was saying, now we're going to talk about a few rules for limits, and we're just kind of going to blow through these. I'm not going to prove them all, but we do need to sort of know these in order to go through and do some other fun stuff this unit. When I say fun, it's not really going to be fun, but that's fine. So the first rule is the limit of a constant is the constant. So if I'm looking for the limit as x approaches any number a of some constant, it's always the constant. The limit as x approaches 3 of 7 is 7. The limit as x approaches -4 of 10 is 10. Right? The limit as x approaches pi of 1,000 is 1,000. Nothing tricky about it. It doesn't matter what value you're approaching. If it's just a constant, the answer is just that constant. Everybody good there? All right, now, given that the limit of two different functions, f and g at a, both exist, then all of these fun and exciting rules are true. If we have the limit as x approaches a of f plus g, so let's say that's x squared plus x, right? I could separate that into two separate limits. The limit as x approaches a of x squared plus the limit as x approaches a of x. So limits can be separated out using addition. They can also be separated out using multiplication. If I have two functions being multiplied by each other, for example, if I have the limit as x approaches a of, we'll say x squared, that's two functions together, right? X times x. I could say that's the limit as x approaches a of x times the limit as x approaches a of x. So they can be separated using multiplication. They can be separated using division, right? If I have one function divided by another function, for example, a rational function, I can separate them using division as long as the bottom one is not equal to 0, right? Since we can't divide by 0. I'm going to skip this one for a second. They can also be separated using subtraction. Not sure why I have the subtraction one not up there with the addition one, but that's fine. Right? You can also separate them using subtraction. And then this last one down here, well, it's not the last one, I guess, second to last one, but the last one we're talking about, allows you to pull a constant out of a limit. So if I have a constant times a function, I can take just a constant piece of it and pull it out to the front of the limit. And this is going to be an exceptionally important rule to us. They're all important, but this one we're going to use hopefully today if we get done with enough stuff. So let's see here. If I had something like the limit as x approaches 3 of 5x to the 4th power, if I wanted to, and there's no real reason to for this particular one because I could just plug in 3. But if I wanted to, I could take that constant and take it out in front of the limit and rewrite this as 5 times the limit as x approaches 3 of x to the 4th. Everybody okay with that or no?
Yes.
Yeah, any questions on any of those little limit rules that we're gonna use later? I'm sure they don't seem very exciting or interesting or helpful to any of the limits that we've done so far, and they're not, but they will be exceptionally helpful soon. All right, another important one is that, you know, anytime we have x to a power, we can just plug it in. We should know that because we should just be trying to plug it in every time. But if I have a function to a power, so let's say I had the limit as x approaches, I have one written down here. The limit as x approaches 2 of 3x plus 4 to the 5th, that's a function, 3x plus 4, being raised to a power. I can, if I want to, rewrite this as the limit as x approaches 2 of 3x plus 4, get that answer, and then raise the whole thing to the 5th power. Now, obviously, in this particular instance, that's not super helpful, right? Plugging in 2 and then getting 10 to the 5th is pretty easy. It's just as easy as plugging in 2 here, getting 10, and then finding that and raising it to the 5th power. It's the same thing. But there will be some really good reasons why we want to be able to pull this power outside of the entire limit. So this is another rule that you're going to for sure want to know and remember and recognize. Everyone good there or no?
Yep.
Perfect. Okay, next one has to do with radicals and rational exponents. All of what this is saying is that anytime you have a rational expression, or a function with rational exponents, all you got to do is plug it in. And as long as it doesn't come out to something indeterminate, you're good. Plug it in the number and you get an answer. You can take the power that's on here and take it outside if you want to. You could even do the same thing with the fractional power of the root. I could say this is the limit as x approaches a of just x, and then to the power of m over n would also be fine. Everybody good there or no?
Yes.
Cool. So just for fun, let's do this limit. It looks unpleasant, but it's not. In fact, why don't you guys take like 30 seconds and do that limit? Ready to go. Okay, to the 2/3 power, we should just plug in 2/3 plus 3 root 8. News is that the denominator is 2. So I think 2. The only reason I'm here is you guys do things like power of 2/3. If you can cube root the number, do that first. So what's the cube root of 8? Should be 2, and then you square the 2 to get 4. And then 3 root 8, you should get to rationalize root 8 into 2 root 2, so that becomes plus 6 root 2. Divide both terms by the 2, and you get 2 plus 3 root 2. Is that what you all got?
Yes.
Should be pretty easy.
Yeah.
All right. Now, those are all of the cool little rules that we should know. We're going to get into our first real theorem of the year. And if you don't understand what I'm talking about with this theorem right off the bat, please let me know, because we're only going to spend a few minutes with it, but I want to make sure you all conceptually understand what I'm saying here. So this theorem is called the sandwich theorem, or it's called the squeeze theorem. It kind of has two names. And this theorem only applies if we can have three different functions, of which one of those functions, and in this case, the way I've written it, h of x, is sandwiched between the other two, f and g, so that on some open interval containing an a value, okay, that f of x is less than or equal to h of x, which is less than or equal to g of x for all the x's in that open interval with a, except maybe at a. The only reason we say except maybe at a is because maybe these functions are not defined at the a value that we're talking about. Okay, so everybody good with having one function that's bigger than another function that's, bigger than another one? I guess I said that backwards, but one function that's less than another one that's less than another one, so that it sort of looks like this, that they're all, one of them is always between the other two.
Yes.
Okay, so then what we would say, according to the sandwich theorem, is if the lower function, f of x, has a limit as x approaches a of some number L, and the upper function, g of x, has that same limit at x as x approaches a, then that means that the one that is sandwiched between them also has the same limit, right? Which I think should make sense, because if h is always stuck between f and g have the same limit at some number, well, h certainly couldn't be above that, and it certainly couldn't be below that. It would have to be sandwiched right in between there and have that same exact value for the limit. Does that make sense or no?
Yes.
Anybody have any questions or concerns about that? Because we're going to use that and apply it right now-ish in about 30 seconds if nobody speaks up and says they have a problem. It's kind of like a wedding, you know, speak now or forever hold your peace. If you don't get it now, it's going to be too late. Not really, but y'all are good? All right. Let's use that theorem to prove that the limit as x approaches 0 of x squared times the sine of 1 over x squared is equal to 0. So first thing we need to do is just plug in 0. So let's plug in 0, right? Because that's normally what we would do for any limit. I know it says use the sandwich theorem, but we're just going to plug in 0. What do you get? You get 0 squared, which is 0, times the sine of 1 over 0. What's the sine of 1 over 0? Well, first off, what's 1 over 0?
I'm guessing the sine of 1 over 0 is 90 or something degrees,
No.
or
Well, what is 1 over 0?
Undefined.
infinity.
1 over 0 is undefined, right? We might say that it's approaching infinity. And what happens to the sine function, and we'll talk about that later, but what happens to the sine function as it goes towards infinity? Well, it goes up and down and up and down and up and down, right? Just oscillates back and forth like a sine function does. Yeah? So is there one specific value this is approaching?
No.
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 So we have something that's undefined times 0. Well, it can't, even if it's just 0 times something that's undefined, it can't multiply by an undefined. Even if I'm multiplying it by 0, that doesn't make it 0, unfortunately. You just can't do something times an undefined value. So that's a big problem. So we're going to have to use the sandwich theorem, like the problem says that we need to. So we need to find a function that is always greater than or equal to this function, and a function that is always less than or equal to this function. And both of those two functions have to have the same limit at x as x approaches 0 in order for us to be able to solve. So I think our best bet to start is if I throw up as us here and we take a look at sine of 1 over x, right? We looked at fairly similar to this the other day. Weird things are happening. Let's zoom in a bit. Somebody's unmuted. Mute yourself unless you're asking a question. That'd be helpful. Cuts down that background noise. Thank you. So we got x squared sine of 1 over x squared. It certainly looks like the limit is, and if I zoom in even more, what does it look like that limit is? Sure looks like it's coming down to
0.
0, doesn't it? Right? Sure looks like that. Which we know it is because the problem said show that the limit is 0. But in order to do that, we've got to find some function that is always greater than this, right? Always greater than this function, but has a limit as x approaches 0 of 0. And we got to find another function that's always less than or equal to this function that also has a limit as x approaches 0 of 0. Any thoughts on those functions?
Can you increase the magnitude of the sine wave so that the peaks of the waves is bigger?
I could. You may just throw like a coefficient out there, you mean like this? Well, I guess I'd have to do it down here. Like this? Is that what you mean?
Yes, but it's not correct.
Yeah, I mean, yeah, so it's, if we zoom in a little, well, it's hard to see, but Yeah, these are going up higher, but that doesn't mean that this one is always, 2x squared sine 1 over x squared is not always more than or equal to this other one, is it? Sometimes it's less than or equal to it, then it's more than or equal to it, then it's less than or equal to it. And that's going to keep repeating forever as these little oscillations come in here. So that's not going to work out. It's a good idea, but it doesn't end up working out.
Could we use two parabolas?
All right. Where did you come up with two parabolas from?
My brain.
From your, that's a good place. All right. What parabolas are you talking about?
Well, just to start, x squared and negative x squared.
Okay, here's x squared. Oh, look at that. That sure looks like it's always greater than or equal to this function, doesn't it? And negative x squared also sure looks like it's less than or equal to this. And amazingly, it actually like really nicely lines up with each of those peaks, right? It hits that parabola and the bottom parabola nice and perfectly. If I zoom in, yeah, it sure looks like it's holding right there above those, doesn't it? Sure looks like it. Oh, I didn't need to zoom in further. I meant to zoom back out. Kind of cool, right? It looks like it's definitely doing that. So, unfortunately, having something look like it's doing it and being certain that it's always above or always below are two different things. So is there a way that we could prove that x squared and negative x squared are always greater than or equal to or less than or equal to this function, using some knowledge we have about the sine function? They are, you're right, those are the exact functions we want to use. But I want to algebraically prove that this is true. Who was that came up with those?
Ben.
Ben, nice job, Ben. All right. What do we know about any sine function? If it's just sine of some angle, whether it's 1 over x squared or x to the 1,000th power, what do we know about sine?
Its range is -1 to 1.
Correct. So no matter what, the sine of 1 over x squared is always less than or equal to 1 and greater than or equal to -1. We would all agree with that, I think?
Yeah.
Yeah, and so this is just an inequality. And what I really want is to have x squared sine of 1 over x squared inside of there. So I'm just going to put it inside of there, which means that I multiplied the middle piece of this by x squared, which means I need to multiply both the left and the right pieces by x squared as well. And there you have it. There's the proof. We know that sine has a range of -1 to 1, no matter what the argument of the sine is, right? The argument is just the thing inside of the parentheses of the sine. And so multiplying it by x squared gives us this inequality that we know to be true. Everybody good there or no? So far?
Yes.
Is that a yes or a no?
Yes.
Silence. Okay.
Yes.
All right. So then according to the sandwich theorem or the squeeze theorem, if the limit as x approaches 0 of this one and this one, the upper and the lower functions are the same, then it's the same limit for the middle one. So now we just need to say, well, the limit as x approaches 0 of -x squared equals what? What is that? It is
X, which is x squared sine yeah.
well, what's this limit? What's the limit as x approaches 0 of -x squared? What are you supposed to do? Plug in the
Plug
Zero.
in the 0 and get 0.
0, right? Which is the limit as x approaches 0 of x squared, right? It is also
0.
0. So we'll say by the sandwich theorem or the squeeze theorem, I can abbreviate it with ST no matter which one I'm using. The limit as x approaches 0 of x squared sine of 1 over x squared is also equal to 0. Any questions on that? Or everybody okay with that?
We're good.
All right. So let's use that same sandwich theorem to prove that the limit as x approaches 0 of x to the 4th cosine of 1 over the cube root of x is also equal to 0. Should we look at the graph of it, or do we have a good idea of what to do here?
Can we look at the graph?
Sure, we can look at the graph. So what did we have? We had x to the 4th.
We're not looking at the graph.
Oh, sorry. I went to it, but I didn't share it. All right, x to the 4th cosine of, what was it? 1 over the cube root of x?
Yes.
All right, so. Great. There's x to the 4th cosine of 1 over the cube root of x. We're gonna have to zoom in here to. Yeah, that's not so helpful, is it? Can't really see that because of this x to the 4th makes it pretty steep, and the 1 over the cube root of x makes those really tiny. Wish there was a way for me to like zoom this in. No, not that way. Maybe if I do this, will that help? No, that's not making it any better. This should make it maybe slightly better. We're gonna stretch this way out this way and then zoom in. No, that didn't help either. Darn. I don't normally show the graph of this one, but it's you can't see it because they're so tiny, but there's tiny little oscillations in here. Sorry, whoever wanted to see the graph, that's not very exciting. But what do we think should always be above it, and what do we think should always be below it? We know about the cosine function. It's always less than or equal to
X.
Less than or equal to 1 and greater than or equal to -1.
right, exactly. Which tells us that negative x to the 4th is always less than or equal to x to the 4th cosine 1 over the cube root of x, which is always less than or equal to x to the 4th. Good or no?
Yeah.
I'm just confused on the way you got from the -1 to the -4. So how'd you replace x to the 4th from 1?
All I did was just multiply each piece of this inequality by x to the 4th because I needed to have an x to the 4th in the middle. And so I said, well, I'm just going to put it in there by multiplying each piece by x to the 4th. So -1.
Oh, okay, thank you.
Yeah, good. Okay.
Yes.
All right, so then now we'll just look at the limit as x approaches 0 of negative x to the 4th, which is
0.
0.
and the limit as x approaches 0 of positive x to the 4th, which is also 0. So by squeeze theorem or the sandwich theorem, the limit as x approaches 0 of x to the 4th cosine 1 over cube root x is also 0. Good or no?
Good.
All right. Now, you're all going to look at me like, why are we doing a third one of these? This is making perfect sense, and it's so easy now. Why would we do a third one, right? That's what you're asking me now?
Yep.
Yeah, well, the answer is because I'm going to confuse you all by doing a third one now. So let's do a third one. First off, this looks very similar to the other ones, right? It's x cubed sine of 1 over the cube root of x, right? We had x, whatever, x squared sine of whatever, 1 over x squared, x to the 4th cosine of something. We should probably do the same process here, right? The sine of 1 over the cube root of x is always between
1 and -1.
1 and -1. Now, what should I do next?
Multiply the whole thing by x cubed.
Multiply the whole thing by x cubed. That's right. But there's a problem. And what's the problem with multiplying the whole thing by x cubed?
It doesn't always, it's not always greater than sine of whatever, because the function goes down and up. It doesn't just, like, you know.
Right. X cubed is not of the same nature of x squared or x to the fourth, where it's always positive or always, well, x squared was always positive, right? And x to the fourth was always positive, but x cubed is not always positive. It's not always above the x-axis or below the x-axis. So, and there's a problem with multiplying inequalities by things that are not necessarily always positive, right? We're going to have to split this up because there is a split on when x cubed is greater than 0. When is x cubed greater than 0? If x is
Positive.
Positive.
and when is x cubed less than 0? Oops, that's not a cube. There we go. If x is less than 0, right? So we're going to have to split this up into two different cases, which is going to complicate things a little bit. So we're going to say if x is greater than 0, then when I multiply each piece of this by x cubed, I'm multiplying by a positive and everything in the world is good. Negative x cubed is less than or equal to x cubed sine of 1 over the cube root of x, which is less than or equal to x cubed. But if x is less than 0, what happens? When I multiply by x cubed is negative, which means what happens to each of my inequality signs?
They all flip.
They all flip. So we're going to say greater than or equal to x cubed sine 1 over the cube root of x, greater than or equal to x cubed, which doesn't seem like a huge deal, and it's not that big of a deal. But it does mean that we have restrictions on our domains for our new inequalities. And we have to think about finding limits with restricted domains. If I'm looking for limits when x is greater than 0, well, what's the only kind of limit I can do as x approaches 0 if x is only greater than 0 for this inequality?
One-sided limits.
It's only a one-sided limit, and I have to do it from which side for this one in red?
The right.
From the right. So I'm going to say the limit as x approaches 0 from the right of negative x cubed is
0.
0. And what about the limit as x approaches 0 from the right of x cubed? It should also be
0.
Therefore, the limit as x approaches 0 from the right of x cubed sine of 1 over the cube root of x should also be equal to 0. And over here, since we're doing x is less than 0, we'll have to do limits as x approaches 0 from
The left.
the left, right, of negative x cubed, which is 0. And that should be the same as the limit as x approaches 0 from the left of x cubed, which tells us, right, that the limit by the sandwich theorem, the limit as x approaches 0 from the left of x cubed sine 1 over cube root of x is also 0. Which tells us what? Because the limit on the left is 0 and the limit on the right is 0, that tells us that
The limit is 0.
the limit of the full function, the two-sided limit, is also 0 because the limit from the left and the limit from the right are equal to each other. Everybody okay with that? Everybody cool with putting all that together?
So the only reason that you knew to do the piecewise, not piecewise, but like that type of thing,
Yeah, effectively it's piecewise, yeah.
piecewise, okay. The only reason you knew to do it piecewise was because the odd exponent, the odd power.
That's correct. Yep. If the thing that I was multiplying by could potentially be negative, I have to take that into account. And since it was an odd power, it could potentially be negative. Everybody good or no?
Good.
Any questions, or is everybody all right? Okay. I think we will stop there.